I wanted to give another update on Alex's spinal cord lesion. We've got some new analysis tools available, which is giving some incredible data and insight, and it's really showing some remarkable trends. And the data is actually very hard to believe, and at the same time, some of these fits are so incredible that it's hard to ignore them at the same time. So let me first by talking about the new software tools that we're using. It's called the Spinal Cord Toolbox, and it's used for automated volumetric analysis of the spinal cord. It's open source software. It's been in use since 2014 and continues to be developed and improved. Uses machine learning to identify the cross-sectional area from the MRI raw data files, the DICOM files, and it's been cited in hundreds of times in medical research. So it's very legit software, and I'm finding it's quite extraordinary in its capabilities. So just some examples of what the output can do, and here's some examples of some of Alex's MRIs, and you can see here where in red the software is highlighting where the spinal cord is, which it uses to compensate the cross-sectional area measurements for the angle in which the MRI slice is based on the setup. And this section here is where you can see each of the individual axial views of the spinal cord, and the red highlights what the machine learning algorithms have identified as the cross-sectional area. And you can see it's quite good. It's not perfect, but I'm finding it's better than the human eye can do. And what I'm most pleased with is that it takes out any potential dad bias that may be in place when I was doing this manually. So let's look at the data. All the data from here on now is from that spinal cord toolbox, and this graph on the right shows each data point is one of the MRI sequences that has occurred, and this is the expansile volume coming from that spinal cord toolbox. And this expansile volume is the difference between Alex's cord volume in the area of that lesion, subtracted out the volume of a healthy control. And looking at both pre-standard of care treatment, and then although you see the change occur as standard of care, there's both the chemoradiation period, which occurred in September and early October, and then the adjuvant TMZ cycles that have occurred since. Again, no human tracing of these MRI images, so this is all data that's non-biased coming from those machine learning algorithms. So as I started to look at this closer, just to see what else we could do with the data, if there was any more insights, something extraordinary popped out. So let me explain what I did. The chart on the left is the same one from the previous slide, and the chart on the right represents the expansile volume change. So the rate of change between each subsequent MRI sequence. So for example, between the March and April 25, those two MRI sequences, if you look at the total volume change divided by the total number of days, you can get the change in volume, the rate of change in cubic millimeters per day. So that's what that first data point represents. And then the next data point would be between the April of 25 and the June of 25 MRI sequences. And here you can actually see that that rate of change actually went down. So it was now at 5.5 or so cubic millimeters per day size change. And then each of the subsequent data points represent all the other differences between the MRI sequences. So you can see that anything larger than 0 on this chart represents that expansile volume was increasing, and negative values mean that volume was decreasing. And you can see the dramatic effect that time period, including chemoradiation, had, and that you can see obviously from the chart over here is kind of the biggest change sequence to sequence. So that's obviously the large negative change in volume. But if you go back to this overall trend outside of that one data point, which is obviously a very known reason why that occurred, the growth rate was decreasing prior to standard of care treatment, and the tumor is now shrinking and shrinking faster and faster. And all of those rates of change all fall on the same line, essentially. That I find absolutely extraordinary. And I really believe there is something biologically behind that fit. So just as another way to view this data, knowing that they all fit, that those slopes all fit on this same line, it means that if you adjust for the chemoradiation time point, then all of this data should fit on one quadratic fit. And so that's what the next slide I'm showing is. Here is all the same data points, and the orange represents the same post-start of chemoradiation, just shifted up by 560 cubic millimeters. What was the reason for the shift? It just represents that there was a dramatic change once chemoradiation started. But once that constant shift is put in place with all of those, all 8 of these data points fall on one single quadratic fit with an R squared of greater than 99.7%. That is extraordinary. And it's so extraordinary that, again, I think it's not an accident. I think there is some explanation for this. I did, determine that shift empirically just for those 4 data points. But again, it was constant for all 4 of them. And another way to think about the exact same thing is like I had on the previous slide. The fact that all of these rates of change over time fall on the same line, that's really the exact same point. That's really the exact same meaning, same point of discussion, that they all fit on this same quadratic fit. So again, I think it's a quality of fit for 8 data points. So again, it would be like 5 degrees of freedom that's rarely seen in the real world. So I believe there's something to it. And the other thing that's really surprising too is thinking about each one of these data points came from a different MRI machine with its own set of parameters. So there's subtle differences in there. The fact that you don't see more error around that fit is another extraordinary thing to take out of this data. So again, trying to figure out what it means biologically, because it could be an important clue moving forward. We have some thoughts. So I'll just leave each one of these slides up with our thoughts. And you can pause the video and look at them in more detail. So this first slide would be, hey, what are explanations that could explain all the data as one continuum, recognizing there was the shift at chemoradiation start? The next 2 slides would be, all right, if you break it up in the pre-standard of care start of treatment and then post-standard of care, and think about it as 2 separate curves. Again, it wouldn't explain why they can all be fit on one solid line, but there's other ways to think about it as well. So there's the prior to standard of care potential explanations, and then possible explanation for post-standard of care. A couple things that seem hard to explain with the data. What we're seeing is that the rate of shrinkage is actually increasing the farther away we get from chemoradiation. It seems unlikely that effect would actually accelerate the farther away in time you get there, so that seems hard to explain. And again, I mentioned just, it seems like there's very little error with the machine differences in the MRI and the settings, and as well as the machine learning algorithm, calculating that chord. So maybe it suggests that those errors aren't as large as I would have estimated at the beginning. Finally, I'd like to call out my son, Kyle. A big thank you. This would not have been possible without him. I had been talking to him, I knew this software existed, but Kyle really encouraged me to go find that software and take a closer look at it. And secondly, he installed it on the computer and put a codex front end in place so I didn't have to learn all the terminal line codes to be able to drive it. So thank you to Kyle to make all this possible.